Greetings, welcome to Chapter 3, Section 4. Now, part of the rationale for the previous video, the Chapter 2, Section 4, and learning about a discrete random variable is because the binomial random variable is a discrete random variable. It's a very important class of random variable. It gets used quite a bit. That and the normal are probably our two most commonly used random variables and their corresponding distributions. So we're going to take a little bit of time to learn a little bit about the binomial random variable. So what is the binomial random variable? Oops, wrong direction here, sorry about that. Well, first of all, we got to talk about something else first, because a binomial random variable is made up of a bunch of Bernoulli random variables. So first thing is we got to define what do we mean by a Bernoulli random variable. And if you got some spare time, look up Bernoulli in Wikipedia sometime and you'll find there was a bunch of those Bernoullis around there in the day making all sorts of crazy madness. Anyway, a random variable that has exactly two possible outcomes, which we will define as being either success or failure. If you have it in such a way that those successes or failures or probabilities remain fixed, then the experiment is repeated under identical conditions, and the random variable is called dichotomous or Bernoulli. So basically, what the fundamental idea here is this. So let me come down here with an arrow here, is that a binomial random variable, is we're talking about this particular random variable, is one in such a way that you have only two possible outcomes, only two things that can happen. It's either going to be a success or it's going to be a failure. So in the case of our previous example that we were just working on, in the previous video, there were only two possible things that could have happened. We could have got a heads when we flipped a coin, or we could have got a tails when we flipped a coin. In the case of that video, a success would have been a heads and a tail would have been a failure, because the random variable was defined to be, hey, count the number of heads. Tell me how many times you see heads, okay? So that would be what we would consider a Bernoulli random variable. So if I did multiple renditions of a Bernoulli random variable, and if you think about that, we did three flips of the coin, then I count the number of successes that occur in each one of those sets of Bernoulli trials, then we create what is referred to as the binomial random variable. Okay, here we go. So a binomial random variable is a random variable x in which the total number of successes in n independent Bernoulli trials on which each trial the probability of success is p, and we say that x is distributed by b with an np. Just as a quick contrast here, remember we had n with mu by sigma. In other words, we had a normal distribution with a mean mu and a standard deviation sigma, and everything we needed to know about that particular normal distribution was given by the two numbers mu and sigma, by those parameters. Well, the same thing with the binomial random variable. It's going to be the two things you need to know is how many times did you flip the coin and what was the probability of success on each individual flip of the coin. So what was the number of Bernoulli trials and what was the probability of success on any one individual trial, okay? So let's think about this in terms of what could happen here, okay? So our random variable x, which turned out to be a binomial random variable in the previous example, well, the random variable, the possibilities that it could take on were what? They were 0, 1, 2, and 3, right? And then we had the corresponding p-values, or their probabilities, of 1/8, 3/8, 3/8, and then 1/8 respectively, right? So we know that in a discrete random variable, there are no values in between any one of these. And so it turns out that the binomial random variable, this is a discrete random variable, okay? So this is discrete. And what that means is that there are no values between 1 and 2, or 2 and 3, etc. Okay. All right. So let's take a look at how this would look notationally. Well, let's think about this for just a second. What was the probability of x being equal to 0, which means no heads? Well, we could think about that by just replacing the x equals to 0 by the actual outcome of the random phenomena there. That would be what? That's the probability of tails, 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 right? Which we knew came out to be equal to 1/8. Okay, well, what if I asked you for the probability of x being equal to 1? I'm going to come over here for that. Well, the probability of x being equal to 1 Well, what do we know that's going to be? Well, that's the same thing as the probability of, well, now wait, there's more than one way that could have happened. That could have happened as tails, tails, heads, tails, heads, tails, right? Or it could have been heads, tails, tails. And so now notice that really what happened here is there were three ways, each of which had a probability of 1/8. So this was 3 times 1/8, or as we came out earlier with our earlier example, is 3/8. So that's the fundamental idea behind a binomial random variable, in that what we know is going on with it is that there are two things happening. There's the probability of any one particular event occurring times the number of ways that it can occur, okay? So we know, for example, the probability of x being equal to 2, that's the same thing as that saying that's the probability of heads, heads, tails, or heads, tails, heads, or tails, heads, heads, right? And notice again, there are 3 ways that that can happen. So if we count here, there's 1, 2, 3 ways. So that's the first number I'm going to write down, times the probability of any one of these particular ones occurring. Well, I want to dissect this even a little bit more. Let me change colors here for just a moment, if it'll allow me. There you go, thank you. So if I change colors here, we're going to make these two red, okay? So these guys are going to be red. In this case, since all of them are equally probable, it kind of is going to seem a little bit silly why I'm writing it this way, but you'll understand in a moment when the probabilities are not the same why you have to do it this way. So the probability of getting 2 heads, well, what is that? That's 1/2 quantity squared. It's h times h. And then let's go ahead and do tails in this beautiful shade of blueberry here, okay? And that's going to be times the probability of not getting a head, so getting a tail, which is again 1/2, okay? So as it turns out that if I want to do a binomial probability, there are basically 3 numbers involved in it. There's going to be the number of ways that it can occur. That's where the 3 is, okay? So that's the first number that we need to know. And then we need to know what? We need to know the probability of success. So this is success right here. And that's going to be raised by the number of successes that happened, okay, which in this case was a 2. And then we need to know what the probability of failure was. In our case, it was 1/2. In other words, what's the probability of not seeing what we wanted to see? And that was being raised to the first power. Now, a key thing that we need to keep in mind here, that's going to be hopefully a little more evident as we actually come to the formula here, is that these two guys right here, they have to sum up to the total number of trials. In other words, that has to be the same as the number of trials, okay? So those two numbers together, the 2 plus 1 has to be equal to the number of trials. All right, so if you've studied a little bit of college algebra, you may have seen the binomial theorem, which was just a quick aside, not too long into this, it was how do I take something like a plus b and multiply it to the nth power? And as it turns out, the coefficients in the binomial theorem are exactly these, we calculate exactly the same way as you did these binomial probabilities. More about that if you're interested, okay? All right, so here's the stunning formula that I've more or less heuristically developed in the previous slide. Here are my 3 numbers again. This number right here, that's my number of ways that I can actually calculate it. That's my probability of success raised to the number of successes I was looking at in that particular moment. And then this is my probability of failure. Right here, that Q, that's my probability of failure, and that's raised to the n minus x, okay? So a couple quick things before we move on here. I'm not going to belabor this because fortunately for us, of course, our studio in R has this formula built into it. We don't need to memorize it. But a key thing that is very important is that P plus Q has to be equal to 1. So the probability of success plus the probability of failure have to be equal to 1. When you're working with a Bernoulli trial, it's one of two things. It's either a yes or a no, a true or a false, a success or a failure. And there are only two ways to split up the probability in each one of the Bernoulli trials. So the sum of that always has to be equal to 1, which leads us to the fact that the probability of failure Q many times is going to be written as 1 minus P. Notice that those are the same thing. So that 1 minus P, we could substitute that right in here for Q and we get the exact same formula, all right? Notice that that's also stated down here. Okay, all right, so that's enough of this because we're going to actually not going to use this formula in that form. We're just going to say, hey, you know what? Our studio's got this built into it. We'll just let it take the hit, all right? But nonetheless, let me show you our glorious textbook's rendition of it, slightly different than what I had in the previous slide. The n choose k, for you folks, if you happen to have, again, a little bit of college algebra background, that's how you calculate that. You may or may not remember that. But more importantly, the mean, the variance, and the standard deviation of the binomial distribution are given by these formulas down below. These guys need to show up in your comp book. The formula up here, that does not, but these do, okay? So these all need to be in your reference book. And label them as the mean. This one here is the mean, the variance, and the standard deviation of the binomial distribution. And make sure you got those in there. Those are going to be important things. We're going to need those a little bit later down the line, okay? All right, so now you come across a randomly selected problem and it's thrown at you and you want to know whether or not is it a binomial experiment or not? How can you tell? Well, the way you can tell is by checking these four little things, all right? So there are four little litmus tests, so to speak, to decide whether or not it's binomial. The first one is that the trials have to be independent. So go back to our flipping the fair coin. Each time you flip the coin, the output of that flip has nothing to do with the next one. In other words, they're independent of each other. Knowing what happened on the last flip of the coin tells you nothing about what's going to happen on the next one. The number of trials is fixed. Yes, we had 3. So every time you look for a binomial, you got to have a fixed number of Bernoulli trials. In our case, with the example we're working on, I had just 3 of them, okay? Can't have an infinite number of them. Each trial outcome can be classified as success or failure. Again, if it's not Bernoulli, you shouldn't be doing this, right? And the probability of success doesn't change from one to the next. In other words, you don't slip in a different coin halfway that's got a different probability of success and failure. So you check off each of these 4 things and you can tell me whether or not it's binomial or not. Okay, so again, this stuff down here, this tip, that belongs in your reference book also in the section on the binomial distribution. So when you get a problem, you can look at it and go, okay, is this binomial or not? And you go, list through these 4 things. Oh, yes, it must be because it fits the pattern. It does each of these 4 things, okay? All right, so one more time. Mean and the standard deviation of the binomial random variable. Of course, if you wanted to, you can replace that with Q. The 1 minus P and Q are the same thing. They're interchanged quite a bit. You got to get used to sometimes seeing as the square root of NPQ. Most times I, to try and stay consistent, use the square root of n times P times 1 minus P, okay? Alrighty then, let's get after some problems. So these are from the textbook. This is Underage Drinking Part 1, Substance Abuse and Mental Health Services Administration estimates 70% of 18 to 20-year-olds consume alcohol beverages in 2008. And they give us the cite, the source there. Okay, so we're going to go ahead and open this up into our studio because we're going to actually do the calculations. We're going to do some pre-work first. We'll do the calculations in our studio. So let's go ahead and open our markdown file. Call this one assignment 4. Get it going here. Assignment 4, yes, that is me, Mike Butler. Say OK. And then we'll get rid of line 7 down. Don't need any of this other stuff. No Stufen. Okay, cool. All right, so this is going to be problem number 27. And I'm just going to go in and cut and paste it right out of the PDF, okay? So I'll bring that in. Have to do a bit of editing, I'm sure, because it never cuts and pastes cleanly. But heck of a lot easier than typing all that stuff in. Okay, so this is exercise 3.27. I am going to come in though and put a header in. Oops, wrong character. I don't want the ats. I want the hashtags. Put in let's say put in 4 of these and say exercise 3.27. Okay, so here's the first part. They say part A, suppose a random sample of 10 18 to 20-year-olds is taken. Is the use of the binomial distribution appropriate for calculating the probability that exactly 6 consumed alcoholic beverages explain? Okay. All right, so let's go back for a minute here, back to our slide, and then let's go ahead and back up 1 or 2, or back here to our tips. So we have to decide, is it binomial or not? Well, are the trials independent? Are the number of trials fixed? And each trial is a classified success or failure? And does the probability remain the same for each trial? Okay, so let's see if we can answer each of those. Okay, so we're going to come down here, and we're going to put in, we'll see, 1. What was 1 again? One more time. 1 is, are the trials independent? Yes, the trials, not trills, trials, are independent. Well, why do we know they're independent? Well, because they were randomly selected, right? We randomly selected these 10 18 to 20-year-olds. And so if it's a simple random sample, then selecting the first person, the first trial, will not affect the next one. Why? And you could just put in here parenthetically SRS for simple random sample to indicate why the trials are independent. Okay, cool. All right, let's go do number 2. So 2, actually I'm going to put these in parentheses. I like them better in parentheses now that I think about it. I'm going to come back over here and fix this one. Sorry, little stylistic change of mind here. All right, okay, so back at it. So part number 2, what do we know? Let's see, let's take a look. And it says part 2, is the number of trials fixed? And you go, yes, fixed trials. And I'm going to say there's 10. So I'll put that in parenthetically. That's a good thing to know, okay? And then the third thing, what do we know about our third thing here? Well, it says each outcome could be classified as success or failure. And you say, what, drink or not drink, right? Because it says, back up here, it says the Substance Abuse and Mental Health Administration estimated that 70% of 18-year-olds consumed alcoholic beverages in 2008. Let's get rid of the 49 there. That was because of the reference, all right? And, well, is it classified as success and failure? Yeah, well, either they drank or they didn't drink, right? So either drank or not. So yes, that is a success or failure. And let's see, what are we looking for here? In this case, they're trying to find, go back to the problem for just a sec, they're saying 70% of them consumed alcohol. So that means that their success is equal to consume alcohol. Now, you got to be careful. The book mentions this, is that success may not be a good thing, okay? So keep that in mind. Success is consumed. Of course, if you produce alcoholic beverages, then it is, right? We'll just go success is consumed and leave it at that. Okay, and then last but not least, the fourth thing, and that is the probability of success P is the same for each trial. This one's actually kind of a deep question. We're not going to go into it. We're just going to say yes. All right. The reality is that the population is large enough that you're not going to be changing the probabilities by taking samples out of there. But in smaller populations, you've got to be careful because that may not be true. Okay. All right. Let's leave that and let's move down to part B here. It says calculate the probability that exactly 6 out of 10 random sampled 18 to 20-year-olds consumed an alcoholic drink. All right, so let's go back to the whiteboard for that. And let's go ahead and go forward here to the slide. Okay, so how are we going to do that? Well, to calculate this, first of all, what do we know? We know that we took a simple random sample here of 10, okay? So first of all, before we go any further, let's write down our model. So just as with the normal distribution, it's always a good idea to write down your model. And so in our case, it's a binomial random variable with number of trials and a probability of success P. So in our particular case, our model is going to be binomial. The number of trials was 10. They took 10 folks and looked at them, and the probability of success was 0.7. Okay, so with that said, let's draw ourselves a number line. So unlike when we're working with a normal distribution where we draw a bell-shaped curve and we find the area under the curve, we're not going to do that here. It's a counting process. And so the first thing we want to do is list all of the possible outcomes that our binomial random variable can take on. In other words, this is an x number line where x is equal to the number of successes. So it's how many times did I find an 18 to 20-year-old that was drinking, okay? So I could have got, out of my sample of 10, I could have got none of them. I could have got 1, I could have got 2, I could have got 3, I could have got 4, I could have got 5 of them, 6, you get an idea here? 7, 8, 9, or all 10 of them were drinking, a bunch of drunks, right? Okay? All right, now the question that they're asking us is they want to know the probability of exactly 6. So they want to know here on part B, they want to know what is the probability of x being equal to exactly 6. So what that means is, let's come over here and we'll do successes in green. That means we want to know what is the probability of just 6. And the way to indicate that is to draw a number line and just put a dot over the top of 6. All right, so to calculate that in RStudio, there are 2 commands that we're going to need. For a particular value, for a single value, we're going to be using dnorm. Excuse me, not dnorm, dbinom, I'm sorry, oh my gosh, dbinom. Dbinom is whenever you see the word exactly. Make sure you got that in your comp book, okay? That'll make this a lot easier. So when you see exactly, you're going to use dbinom. In a minute, you're going to see where we use pbinom. And the way it works is it's actually pretty straightforward, is that dbinom, let me do it all in lowercase here so it looks how R does it. The way the parameters go in is you put in x, the value that you've got, in our case that would be a 6, and then you put in n, which is your number of trials, and then you put in p, which is your probability of success, and RStudio will go and use that formula we talked about just a minute ago and actually do the calculation. So let's go ahead and do that. So let's go into RStudio and let's open up a chunk. Okay, so we're going to go open a chunk, and then let's come down here and let's put in the command that we just said. So you go dbinom, and then we put in our x, which was 6, we put in our number of trials, which is 10, and we put in our probability of success, which is 0.7. So let's go ahead and run that chunk so we can see what it gives us back. And it gives us back the probability would be about 20% of the time we would find exactly 6 of them, okay? All right, cool. So what is the probability? Exactly 4 out of 10 of the 18 to 20-year-olds have not consumed alcoholic beverages. Give myself a fresh line in the right spot here. There we go. So what is the probability that exactly 4 out of the 10 have not consumed an alcoholic beverage? So we got to think about that, okay? So they're asking us for the 4 out of the 10, okay? So exactly 4 out of the 10 have not consumed alcoholic beverages. Well, that's an interesting question. So let's go back and draw ourselves a number line and see if we can actually make that make sense. So let's go back again to the whiteboard, okay? So this is part C here. Here we go. Okay, so let's draw ourselves yet another number line. You're going to get used to doing these. You get fast after a while. Accuracy important too. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's amazing. As soon as I start recording these things, all of my arithmetic just falls out of my head. Number sense, be damned, I don't have any of that. Okay, so it's an interesting conundrum here because they say, what is the probability that exactly 4 out of them do not consume alcoholic beverages? Okay, well, to not consume alcoholic beverages means that only these guys don't, okay? So they're looking for a probability of failure this time. So I'm going to do failure in red. So what that means is if you come back over here, that means everybody else would have been there. So we were trying to find just the 4, okay? So there's a couple of different ways we could attack this. We could go in and calculate all the other ones, but that's just going to be a lot of work to calculate all these other probabilities and then subtract it from one to get this one. Actually, a much simpler way of doing it is for this one, for this particular one here, we're going to change things slightly and say, well, what would happen? Oops, my bad, it's the wrong color. What would happen if we redefine for just a moment that the probability of success was 0.3? Are you getting it? Does that make sense? Because look, the probability of success up here was 0.7, so success plus failure has to come out to be equal to 1. So to find the probability of the single failure, all I've got to do is go in and calculate it doing it that way. Notice how much easier that will be than if we had come in and said, well, what if I did want to do it the other way? In other words, what if I came in and said I wanted to calculate all of these? Well, you notice that's going to be a lot more work to come in and calculate all of these values, because these are the ones that are a 4. I mean, excuse me, they're not the 4, right? Remember what our question was again. It says, what is the probability exactly, what are we doing here? This is part C again. What is the probability that exactly 4 out of the 10-year-olds have not consumed, okay? So this is the only one to be a failure would be this one. So it's going to be much simpler to calculate this probability than to go through and calculate all of the green probabilities and then subtract that from 1. Okay, enough chatting. Let's go do it. Let's go back over into our studio here. Oh, come on, you silly pen. Okay, so go back into our studio, and what we're going to do is put in a new chunk. So insert a chunk here. And calm down, and it's basically going to look very similar to the last one we put in. We're going to put in d binom, so d binom, and we're going to put in what? Well, we're going to put in 4, not 5, 4, Mike, by 10, and then our probability of success this time, actually the probability of failure is 0.3. Okay, so let's run that chunk. And we get back, look at that, same probabilities we got last time. There must be some sort of treachery going here. I'll let you think about what that treachery is. If you got questions, ask me. I'll be happy to answer them. Let's keep moving though, because we're getting kind of long-winded in this video. So what is the probability that at most 2 out of 5 randomly sampled 18 to 20-year-olds have consumed alcoholic beverages? Okay. All right, now we gotta be careful because they changed it on us, right? Back up here on the previous problems, they said, because what they did here is they changed the game on us, and they said, this time, if you take a look, let me scroll back up here right here, they said at most 2 out of 5 randomly sampled 18 to 20-year-olds. So before it was 10, and now they've changed the n on us to 5. Okay, that's partially because they're thinking you may have to be doing this by hand, and so they were actually trying to be kind here. Although it would have been kind of nice if they'd been a little more explicit about why they did that. Okay, anyway, let's go back to the whiteboard for a minute and let's see if we can set up this new situation. So let's get ourselves a clean whiteboard here. Go back to block on the pen and let's go draw our new model. So first thing we're going to do is change our model definition, because we know now our model is binomial with an n of 5 and a probability of success of 0.7. Okay, so probability of success did not change, but the number of trials did. So now our distribution goes from 0, 1, 2, 3, 4, and 5. Okay, so these are our x's. These are the possible values the binomial random variable can take on. Okay, now what did they ask us for? What did they want from us? Well, they want to know the probability of at most 2 out of 5 randomly sampled 18 to 20-year-olds having consumed alcoholic beverages. So at most 2. So let's think about it. What would that be? What would at most 2 be? Well, it would be none of them drank, it'd be one of them drank, it'd be 2 of them drank. So that would be the at most 2, right? And then the failure parts, that's going to be the 3, 4, and 5. So if we found that there was 4 of them out of the 5 that consumed alcohol, then that would not be what we're looking for, okay? So here's the thing we got to recognize. Let's see if we can make this make sense. This part, all the greens over here, that's the probability of x being less than or equal to 2. And then the red stuff here, what is that? Well, that's the probability of x being greater than or equal to 3, isn't it, right? And what we know about those two probabilities that I just wrote down is they represent everything that can happen in this particular distribution. So the sum of those have to add up to 1, don't they? That's going to be important in a minute. We're going to be in luck in the command that we're about to use because it's going to be a left-tailed command and we're all set up for a left-tailed problem. But that idea, that concept that we just wrote down there, I strongly advise that you look at that every time you're working with an at least or a more than situation. Okay, so key thing here, I'll go back to it in a minute, was they said at least. So if you get an at least in the problem, or you get a more than, or anything that infers an inequality, then what you know that what you've got is that you're summing up multiple parts of the binomial distribution, not just taking a single value. You've got multiple. It's cumulative. So in that case, it's going to be just like when we were working with the normal distribution. We're going to use p binom. And so what p binom does for us is it adds up to the ending number. So p binom is going to work very similar to what we had in the previous problems. Is it's going to be x by n by p. In other words, you put in the number you want to add up to, the number of trials, and the probability of success in any one particular trial. So the probability of x being less than or equal to 2 is going to be p binom. Our x was 2 because that's what we're adding up to. Our n this time got changed to 5. Don't forget that, okay? And then our probability of success, that remained the same. That's still 0.7, okay? Or 70% of little buggers are drinking. Okay, so let's go back into our studio and go ahead and enter that in. Come on now, get in the right spot here. Here we go. Our studio, please. Thank you. Okay, so come down here. Let's go ahead and insert a chunk so we can actually get our stuff in here. Okay, so since it's cumulative, it's p binom. P binom. And let's see, going to put in the 2, going to put in the 5, and going to put in the 0.7 so you don't miss that decimal point. Let's go ahead and let's run that. It comes back to about 16.3% of the time you would expect to find 2 or less, okay? All right, one last one. I'm going to be able to end this video on an upswing. And it says, what is the probability that at least 1 out of 5 of the randomly selected 18 to 20-year-olds have consumed alcoholic beverages? Okay, well, let's try that one. Let's go back again to our whiteboard. We're going to set up just as we've done in all the last ones here, set ourselves up a number line to help us out with it, okay? So let's go ahead and clean this one. Get a fresh board here. All right, so again, it's going to be the same model as in the last problem. Our n is 5. Our probability of success is 0.7. So we're going to have what? 0, 1, 2, 3, 4, 5 again are our possible values of x. And if you read the problem, it says, what is the probability of at least 1 out of the 5 randomly sampled? So at least is just like at most, all right? Except for at least means that this is basically a greater than. It's a kind of a nerd way of saying greater than. Okay, and so that tells me, that infers to me that I would probably want to use p binom, but you'll see in a minute that actually I don't have to here, okay? All right, so let's go color off everything that we want here. What are we looking for? Well, stop for just a second. Let's convert this into the language of probability. This is the probability of at least 1, means the probability of x greater than or equal to 1. So what we want are these values. All these green ones here. We're summing up all of the stuff to the right, okay? And so the one we don't want That's this one right here. Okay, now the p binom is just like p norm. It sums from the left, okay? So let's take a moment here and write down everything that we've got. This is the probability of x being equal to 0. That's what's in the red. And then in the green here, this is the probability of x being greater than or equal to 1. As we just said in the last problem, that we know that the sum of these two have to add up to 1. That's got to be equal to 100% of what we've got, okay? So it actually turns out that the easiest way to do this problem, it's kind of a cool trick, is to say, well, look, what we want, the probability of x being greater than or equal to 1, well, what is that equal to? Well, that's equal to 1 minus the probability of x being equal to 0 by simply solving it, okay? Well, that's cool because this is going to be really easy to calculate, because what this means is this is 1 minus not p norm this time, or excuse me, p binom, but d binom. Well, why d binom? Well, because it's a single value. See, it's got an equal sign. So maybe a really cool trick to think about it is a less than or a greater than, either one of those, greater than or equal to, less than or equal to. Both of those are inferring to me that I need to use p binom. And then in the case where I have an equal sign, what that infers to me is that I'm going to have to use what? D binom for a particular one. It's just for a single value, for an exact, all right? So this is going to be D binom. Well, let's see. How do we go about doing this again? Well, I need to give it the value that I want. Well, that's going to be 0. The number of trials is 5, and the probability of success is 7. Okay, so let's go back to RStudio, and let's go ahead and do that. So go ahead and insert a chunk. If we insert our chunk here, we're going to put in 1 minus d binom. And we're going to put in, let's see, what was it again? Oh, it's 2 by 5 by 0.7. Okay, let's go ahead and execute that. Actually, I'll put a 0 in the front of there. It's just so much cleaner with the 0 in front, right? So let's go ahead and run that chunk. And it looks like it's about 0.8677 would be the probability of it being at least 1. So about 87% of the time when you grab a group of 5 18 to 20-year-olds, at least one of them will have consumed alcoholic beverages. Okay, well, hopefully you're getting the hang of this. The more you do this, the better you get. You get to do a problem just like this in the homework. So if you have any questions, of course, be sure and post the discussions.